Everybody. I am DK Panda from Ohio State University and my colleague Dr. Xiaoyi Lu. So, two of us will be presenting this. So, our work here is focusing on high performance Hadoop and Spark on the OpenPOWER platform. As most of you know, we are in a very exciting phase of going between HPC and big data and deep learning. One field is trying to push more pressure on the other field, and we want to get the new results, and it puts again feedback to the previous one. So, we are in a very exciting loop here, and at the same time we are trying to focus on convergence between these fields, HPC and big data and deep learning, and also there is an increasing need to run these applications on the cloud. Now, when we are talking about big data, so the question is, okay, what is the complexity of the big data? I mean, this is a very interesting chart which is trying to show how much data is being generated every minute on the internet. Okay. It is a little bit of older data in 2016, but if you see like a early part of 2017, just take it like any of the things like a YouTube, there are almost 4 million videos are being uploaded in every minute. Similarly, if you see like let's say Twitter, there are 456,000 tweets are being sent every minute. So, as the intensity is increasing continuously, there is a lot of more and more demand to do the processing. So, how do we do this processing? So, if you take a look at the high level picture of the modern day data center, this is how you will see like when we connect to an internet to a data center, these are the like the front end here and these are the back end here. So, mostly we try to do the online processing like components like NoSQL DB, HBase or Memcached. This is what gets used in the front tier. Then in the back end here, we try to do the offline processing, which are like the HDFS, MapReduce, Spark, etc. So, the question is, how would we design these kind of data centers? And now, especially if you see here, there is a lot of interesting technologies which are going on. I mean, we have the multi-core, many-core, especially the OpenPOWER is fitting into this many-core architecture. We have the InfiniBand interconnect and also the NVIDIA GPUs, and also there is a increasing things what we are seeing with respect to SSDs, NVMe SSDs. So, these are like the combining the InfiniBand RDMA with SSDs kind of capabilities and the NVRAM. So, these are the newer components which are leading to design these modern day data centers. So, these are with respect to the hardware, but the question is, okay, how about the software? And now, if you take a look at like the software, we of course have to take the very best of the hardware, and especially in the OpenPOWER, if you see like the Power 8 architectures, it is not only like having a large number of cores, but with respect to each core, we also have 8 SMTs, so that we can run actually things in a very highly multi-threaded manner, and even within a node, we can have up to 160 threads. So, the question is, if we are trying to design any software stack, we need to make sure that we take advantage of all these threads. Now, this is a little bit of dense chart, but if you are working in the networking technology area, so it might be more familiar to you. This is something, how many of you know like a OpenFabrics software stack? Okay. So, if not, so this is where like just like you think of the Linux gets developed in the Linux community, similarly a lot of network drivers are being designed in this OpenFabrics community. So, here especially if you see like on the left hand side, these are the traditional Ethernet. So, that means we have your application is written with sockets, and it is typically written with a TCP/IP over Ethernet driver, Ethernet adapter, Ethernet switch. So, this is the pure Ethernet. With the InfiniBand, you can also run the sockets based application. It goes through an emulation mode called IP over IB. That is how you run in the InfiniBand adapter, the InfiniBand switch. So, you get the bandwidth, but you may not get the latency. And then of course, there are different kinds of Ethernet adapters with different offload, TCP/IP. So, this is like the TCP/IP offload. But when InfiniBand came into the market, this is what actually is designed. On the right hand side is the native. That means that is where the best performance you get, the lowest latency, highest bandwidth, whatever you will be talking in the slow floor here, like RDMA, all those big benefits happen on the right hand side. But there is a small catch that to achieve all these things, direct sockets cannot give you that. So, that means at some layer of your software stack, you need to modify the sockets to verbs. The verbs is like a very low level network interface in which you need to call. Then what has happened over the years, a lot of software stacks are moving from the left hand side to the right hand side, okay, to give you those kind of benefits. It has happened over MPI, it has happened for parallel file systems. So, the question is like, can this be done over also over big data? Okay. So, this is where like in my group, like in 2 hours back, I gave another talk in another session with respect to MPI and PGAS. So, this is where we have been working for almost last 17 years. Our MPI stack is very widely used, even including the number 1 in the world these days. So, while we were working in the MPI project, we also started looking, this was like another 5 years old project, not 17-year-old project, the MPI is 17-year-old. So, we asked the question that as the field is moving to the big data, how those software stacks can be enhanced, just like what we did for MPI. Can we take similar kind of knowledge and enhance or accelerate these stacks? So, we asked the question, what are the major bottlenecks, how HPC technologies can be used here, can RDM enabled high performance interconnects like InfiniBand or iWarp, those kind of technologies can be used for big data, can even high performance storage systems like SSDs or even parallel file systems. Just like in an HPC cluster, you know, you have Luster, GPFS, those kind of parallel file systems can directly be used. And then if we can use those, how much performance benefits can be achieved, okay? And then how also we can introduce benchmarks to evaluate the performance. So, our broad goal was to bring this HPC big data processing and deep learning into a convergent trajectory, so that people can actually deploy all the software stacks in a very efficient manner. So, what do we mean by convergence? So, let me go into a little bit more details. So, our idea here is that on the same hardware, let us say you have an OpenPOWER platform, OpenPOWER systems with InfiniBand, with GPUs. On the same system, you can run HPC, you can run big data, you can run deep learning. You do not need like multiple versions, okay. So, that is where I am trying to show through animation. So, let us say you have physical compute nodes, you have resource managers like Turk or Slurm, you have parallel file system like Luster and GPFS. Can I run these kind of things concurrently? On a very large scale cluster, might be some nodes are running MPI jobs, some nodes are running big data Hadoop jobs, some nodes can run Spark jobs, some can run deep learning. And those of you who are familiar with HPC stack, sometimes you just submit these as batch jobs. So, same thing you can also do now for big data and Spark. So, all of these can coexist. So, that is our vision, and in fact, we have achieved this. That is what we will be talking here. So, in order to achieve that, we came up with a software framework. So, the software framework has like in the middle, we took like these are all the big data middleware, HDFS, MapReduce, all these things. You will see they have been traditionally using sockets. Like if you download Apache Spark or Apache Hadoop, below at the network layer when they talk to each other is sockets. That is the lowest layer they can go. And then of course, we have all these different technologies I talked about, computing, networking and storage. So, we introduced our own communication and IO library modules here, and first ask the question that can, instead of sockets, can we move to verbs? You remember in the previous slide I showed the verbs is the right hand side. If we can rewrite some of the low level functions, we should be able to directly run with good performance. And that is what we have done. And not only that, once we have done that, now we are actually modifying some of the upper level software stacks, because these software stacks were written with slow network in mind. Sockets is very sockets, TCP/IP, those are very slow, okay. So, now if we can enhance that, then we can explore at the upper level architecture and then enhance them further and then put them together to get even bigger and bigger benefits, and that is what we have done. So, this project is called High Performance Big Data or HIBD. If some of you are not familiar, you can just go to this website. So, we have actually enhanced version, like we call it RDMA, but it has a lot of additional designs in addition to RDMA, RDM for Apache Spark, RDM for Apache Hadoop 2.x, HBase, Memcached, even Hadoop 1.x which is being phased out. So, all these are available, and these can run on InfiniBand, Rocky, it can also run on Ethernet, and these are publicly available. You can just download, and currently just go to this site. We have around a user base from around 275 organizations from 34 countries. These are based on voluntary registration. Many people download, they do not want to identify themselves, that is okay with us, but those who have identified themselves, you will see they are listed there publicly, and then we have more than 25,000 downloads from this kind of stacks. And in addition to these stacks, we also have like a benchmarks. and we'll talk about a little bit about that, how exactly you can evaluate not just on an application level, but just HDFS layer or MapReduce layer or HBase layer. Individually, you should also be able to evaluate. And then this is the kind of like a release time download. As you can see, over the years, we started the release around June 2013, and then in like 4.5 years now, we have been reaching continuously, steadily rising here. And these were originally designed with x86 architecture, and of course, as the OpenPOWER architecture is coming, we have tried to enable these in our public releases now support OpenPOWER. So here example, like this is like a feature list. I don't want to go into more details. We'll see some of the features and numbers a little bit later on. So in fact, now we enable actually OpenPOWER support here. And the way we try to do it, if you see, this is based on like Apache Hadoop 2.8, which is the latest public stable release. And the main thing is that this is compliant. That means we don't change any APIs. Many people think that, wow, you might have done some API changes to get the performance. No, we keep the same APIs. So whatever runs publicly with Apache Hadoop 2.80 or Hortonworks or CDH, it will exactly run on our system. Okay, our stack, there are no difference. And in fact, I forgot to mention one thing here. We also have some plugin designs. You know, in the big data work, like sometimes people use the Hortonworks stack or Cloudera stack. We don't want you to throw those things out. We have developed some plugins for those stacks. So you continue to use those stacks, but use our plugins so that the networking part is being accelerated. Okay, so that is the kind of our architecture. So this is like the broad overall view software architecture you can see. So we'll go into a little bit more details later on. Like Hadoop, you know, there are different components. One is the HDFS component. So we have some different versions here, like we have a heterogeneous storage, in-memory mode, even Lustre mode. We have a burst buffer mode. We have also RPC is a remote procedure call, is a big component in the Hadoop. We have also made that RDMA. And also the MapReduce, we also have enhanced it with RDMA and also enabled it with Lustre. And more importantly, we have also interfaced with the job scheduler like Slurm and PBS. So if your HPC environment is just like you submit MPI job, the same thing you can submit Hadoop jobs. Okay, so it's a very unified environment. So that's where we are trying to achieve the convergence. Similar kind of things we have done for the Apache Spark. So this is again, it has a lot of advanced designs. It has support for OpenPOWER. The public release is based on 2.10, which is the very recent stable release, and we support that. HBase, similarly, we have an optimized version. The OpenPOWER is being worked out. It will be available in future. It's not yet released, but it is on the x86. It has been there for many years. Similarly, there is another component called Memcached, which is very widely used in the Web 2.0 environment in the multi-tier data center. That also we have made it RDMA enabled, and there also we are working on the OpenPOWER support. So in addition to all these stacks, we also have a lot of benchmarks. For example, if in the community, if you just want to evaluate HDFS itself, you will see there are not many tools or stacks available just to evaluate HDFS. So to allow that, we actually introduced a micro benchmark set for Hadoop distributed file system. It has sequential write latency, read latency, different kinds of, you can use it to benchmark products from different HDFS solution provider. Or within HDFS, you can go inside and see where the bottlenecks lie. So this helps the developers and engineers to find out where the limitations lies, where things can be enhanced, which you cannot just do by running an end application. Okay, so that is our goal. So same thing we have done for Memcached, HBase, Spark, etc. This is also publicly available. You can download. So with this kind of environment, so what we do is, this is our vision and this is what we have achieved. If you see, like on a given cluster, let's say you have an HPC cluster or OpenPOWER cluster, you can take our, let's say the HiBD stack. It has again different mode. You can, based on your configuration, like what kind of SSDs you have, what kind of file system you have, since you select the appropriate mode, compile it, and then put it as a module. And then let the users just use the module. They don't have to worry about all the internals. Just like MPI library, you just submit your job. Similarly, people will just submit their application, which will run against the Hadoop. Same thing we can do is also with Spark. So in fact, we have been working very collaboratively with San Diego Supercomputing Center. They are one of our collaborators. If those of you are familiar, NSF, the US National Science Foundation, has the Exceed environment. all the supercomputing centers are connected. So on SDSC Comet, we all actually have deployed, like just like you see the RDMA for Apache Hadoop in this path or Apache Spark. So you can just, if you have an Exceed account on SDSC, you just directly use it. There are no issues. Same thing we have also done for Chameleon Cloud. That is a cloud infrastructure from, again, National Science Foundation. We have actually made it available just like an appliance. So as an end user, you just have your job, you take your job and click on the appliance, and then it will just, everything else will be taken care under the hood, kind of things. So with this, let me hand it over to my colleague here, Dr. Xiaoyi Lu. So he will go into a little bit more details and then try to take a look at what kind of performance benefits you can achieve. Because these are the newer stacks. If you don't get performance benefits, what is the motivation? Okay. So that's what he will try to show, and then you will see that it delivers very extremely high performance benefits, and exactly on the same hardware, InfiniBand hardware, using the Apache version. If you don't want to use that and use our version, you get significant performance boost. That's what he will be talking.
Good afternoon, guys. So my name is Xiaoyi Lu. I'm a research scientist in Dr. Panda's group. Dr. Panda has given an overview of what we have done during the last 5 years for RDMA-based designs for Apache Hadoop, Spark, HBase, memory cache, whatever. So actually here, this part I'm going to give a little bit more details of what we actually did in these packages. So first of all, let me introduce what we have done in the HDFS component. As you have know, I mean, HDFS is the major component or major distributed file systems for all kind of different big data analytics stacks. For example, no matter you run MapReduce jobs, HBase jobs, or like Spark jobs, whatever, you need HDFS as the underlying file system. Even these days, when you run deep learning stacks, in order to integrate deep learning into the big data analytics pipelines, you still need to use data which actually stored in the HDFS layer. So that's why HDFS is the most important component. You have to first know, okay, how to enhance it in your cluster if you have multiple machines and high performance networks. So first of all, this is the architecture of HDFS. This is your application based on HDFS client or HDFS API. So by default, if you don't change anything, you actually go through the left side path. Basically, your HDFS is running on top of Java socket library. And then the Java socket library will go through the TCP/IP protocols and then go through either Ethernet networks or IP over IP protocols. But actually, we take this design into another direction. We actually bring the native verb space design into the HDFS under HDFS APIs. Okay, like Dr. Panda mentioned, we don't change anything in the HDFS API layer. So everything all the default communication paths will be bypassed if you enable our components. Okay, we'll go through JNI, redirect your write path to the OCU design, which running on top of native verbs, and then go through the RDMA protocols. And in our RDMA engine, we actually support both InfiniBand as well as Rocky, as well as the iWarp. Actually, today I talked with one person. He mentioned about whether we support iWarp. Actually, we support that. So depends on what kind of network you have, you can enable this. So not only that, in HDFS, there's a very time-consuming phase called replication. Basically, in order to support the fault tolerance, you need to replicate your data in multiple nodes. And in that phase, exactly like a communication intensive or as well as IO intensive phase. So with RDMA protocol, you are able to significantly improve the performance of that. Okay, so we have some papers in some different conferences. If you have interest, some kind of pointers, you can take a look. So this is about the communication part. Actually, later on, we see there's another new opportunities coming up. So for example, in many HPC clusters, including, for example, OpenPOWER cluster today in the keynote talks, we heard a lot of discussions about NVMe SSDs, right? Those kind of new storage also available in these clusters. Now the question is, if you look at the storage perspective, in all these multi-core machines, you will get a lot of different kind of storage mediums. For example, you have RAN disk, you have SSD, SATA SSD, PCIe SSD, NVMe SSD, different generation of NVMe protocols. And then, of course, you have HDD. For example, you have like 6 or 30, up to 32 HDD on each node, probably. And then another important thing, you probably also have another dedicated mount point, which backend by some parallel file systems, just like Lustre or GPFS. Now the question is how you actually can deploy your HDFS and utilize all this kind of different storage medium in the most efficient manner. So if you look at the HDFS inside, right, you definitely need to handle 3 different things. One is how you place your replica, how you place your block in the HDFS layer. What kind of block should put in the high-speed storage? What kind of block should put in the low-speed storage? This is one thing. Second thing is replication, like I mentioned, because you need to provide fault-tolerant support. Now the question is, if you put a run disk, of course, if power is gone, then you lose your data. If you put in Lustre, Lustre has the RAID support typically. So in that case, you don't have to enable the multiple replication in HDFS layer, right? As long as you have one replica in Lustre, you probably can change the replication protocols. So you can do a good trade-off between fault tolerance and the performance. And then efficient promotion, that's another exciting point of HDFS, because your applications, think about deep learning or any other stacks, you definitely have some hot data and some cold data. Now the question is how you efficiently move this data from different level of storage hierarchy, right? So that's another important things, okay? So with all of this, we propose a design called a triple H, HHH, basically means enhanced HDFS with memory and heterogeneous storage. So with triple H, we actually have 3 modes. One is default modes. Basically, we are trying to use all this storage in a balanced manner, okay? And the second mode called in-memory mode. So these days, because if you look at the community, people trying to do in-memory computing. So there's another interesting work in the community called Taikyang or Alex IO. I hope you heard of that. They're also trying to bring the IO purely in memory, so that I give you maximal performance, but in the meantime, I use different techniques to guarantee the fault tolerance as well. And then lastly, integrated, like I mentioned, how to utilize Lustre or GPFS in your cluster. So in that way, you probably can change the replication protocols as well. So that's the HDFS part. And the third thing I want to mention is about the MapReduce. So MapReduce is a different story when you want to use high-performance networks and high-performance storage devices, because in MapReduce, the most time-consuming phase is called shuffle. Shuffle basically means your data needs to transfer from map phase to reduce phase, right? Think about if you do 1 terabyte sort or tera sort, you actually need to move 1 terabyte of data over the networks from one set of nodes to the other set of nodes. That's a big amount of work has to be done efficiently. So with our design, similarly, we don't, again, this is the default architecture. You can do the transfer over the Java socket libraries, either through JT. In default Hadoop, they're using JT, which go through HTTP protocol, which is a very heavy protocol from performance perspective. And then with our approach, we don't change anything in the MapReduce API layer. We just bypass your default design. We bring your traffic to the native verbs-based RDMA protocols, so that we can achieve the maximal bandwidth, maximal throughput, and the reduced latency for your data transfer. Not only that, we also find that in order to improve performance further, you need to do efficient prefetching and caching of map output, so that all RDMA operation comes, the data will be in the memory already. So that's actually another something important. And also shuffle algorithms, in-memory merge, how to avoid disk I/O, those kind of things we have proposed in the whole stack. Again, we have this is the paper we published in ICS 2014. If you have interest, go over this paper, you may get more details. So now, because we're talking about OpenPOWER, right? Recently we did another job. So we bring all these stacks on top of OpenPOWER machines. Now the question is, what kind of new things or what kind of designs, accelerations we can do on the OpenPOWER machines? Now, of course, if you look at this stack, we don't want to change each of the components individually. That's a heavy work, right? Okay, for OpenPOWER, should we do something in the HDFS or MapReduce Spark HBase differently? No, we want to bring some unique design, unified design, so all these stacks in the upper layer can automatically get the benefit out of it. So in the based on our experiments, what we see that the most important thing we need to enhance is actually in the RDMA communication engine. So the multiple things we listed here, just highlight what we have done. So first of all, we want to do an efficient RDMA device selection and the locality detection. So basically, because you have so many cores or SMD threads, and in the because all these systems are based on JVM, right? Internally, they have a lot of threads as well. For example, even one single RPC client just for RPC component, okay, it has like more than, in OpenPOWER machine, has more than 80 threads. Now then you think about if you have MapReduce and you have HDFS, all the things together, how many threads you have? Maybe thousands of threads. Now the question is how you can efficiently make sure that as long as these threads go through the RDMA protocols, they are able to pick up the right RDMA device and also use the best binding policies. That's another thing very important. Basically, in the HPC area, actually binding or affinity setting is very common, but in the big data area, it is still not being well explored, especially in the OpenPOWER systems. So we propose different kind of binding policies so that user can specify, okay, whether you want to bind your communication thread to what kind of course or SMT threads, okay? So in that way, we are able to give the best communication performance. So not only that, actually, in order to bring the like a user easy to use our stack, we are automatically detect these kind of things, and then we automatically binding the communication thread to the cores which closer to HCA. Those kind of policies are actually available. And also another important thing is like a power architecture aware tuning. This is another something we observed. So for example, compared with Intel Xeon architectures, so some internal protocols may need to be tuned. So we have some power architecture aware tuning component inside our library so that we are able to get better performance, like even for this, both our same RDMA design on OpenPOWER machines. Again, like I said, this design actually supports both Hadoop and Spark, whatever we mentioned earlier. In the future, we'll support HBase and memory cache as well. Now let's take a look at the performance, whatever I mentioned about RDMA-based Hadoop on OpenPOWER. So this the yellow line is the IPOB over IB Eastern EDR, which 100 Gbps, and then the red bar is our RDMA IB native design. So the left side is the Triple H default mode, which basically use all kind of storage device I mentioned earlier in a balanced manner. And then HHM mode basically use just purely in memory. So you can imagine that you can get a higher throughput for this test FSL, okay? So higher is better. So as we can see that our RDMA design can improve like almost 2x for the throughput. So basically, if you use the same hardware, you run default Apache version on the OpenPOWER machine, and then you run our version on the OpenPOWER machine, you're able to get 2x performance improvement for the throughput. And then similarly, we run sort in the Triple H mode, default mode, and the Triple H M mode. Similarly, we see that, for example, for the default Triple H mode, we are able to reduce the execution time by 40%. And then for the in-memory mode, we are able to reduce the execution time by 55%. That's like almost half your execution time. And then third example we showed here is like a Terra sort, which is a little bit different than sort from the workload perspective. Again, we are able to reduce time almost 20% or 15%, 12 to 15%, depends on how large of data size you want to test. So the next example is about Spark. So Spark is a little bit different than the Hadoop because Spark is by default is in-memory computing kind of concepts. So they are trying to build some RDD objects and then utilize all kind of memory available in your machines. So of course, if you have large memory nodes, it's definitely helpful for Spark kind of workloads. Again, by default, Spark is trying to use Netty. That's another very like a popular open source library in the Java community. And then NIL is the default Java socket library. So that's the default protocols available in the Spark stack. But we actually provide some plugin in the Spark architecture so that you don't, all these kind of shuffle managers above layers are not changing anything. We don't change anything over there. So all kind of default shuffle mechanisms like sort hash or constant sort is able to coexist or co-work with our proposed designs. We give a lot of advanced features. There's some pointers you can take a look in our papers. So we run some kind of experiments on OpenPOWER machine as well. So this is the group by and sort by. We see that IPOB performance on OpenPOWER actually is good. So our RDMA design is able to give like a 11% or 18% performance improvement for different workloads. But actually, when we go to the this result actually is with NVMe SSD. So with NVMe SSD, we see that RDMA, if you have RDMA protocol, you're able to get a much better performance improvement, like 35% or 25%, depends on different workloads. This is, again, same hardware, okay? The yellow bar is the default Apache Hadoop or Spark. The red one is our solution. So your application is also same. There's no change in application, no change in the hardware. Just the middleware level. You just switch to our version. You are able to get much better performance. So again, in our group, like Dhabaleswar mentioned, we have been working on this area for more than 6 years. So we are trying to do some other things also. For example, we are trying to propose some new designs to enhance performance for both big data analytics and deep learning stacks. We want to, in the nearest future, we want to make HBase and memory cache which can run on top of OpenPOWER efficiently, public available for everybody. And then we're also working on TensorFlow in the Cafe and many others. And we also see that GPU plus Power plus InfiniBand, this may be a very good combination for the future big data and deep learning applications. We're also trying to see what other design opportunities available, probably we can do for the power line. And then some other things like earlier talk before this one, we heard something about like OpenStack or Kubernetes on top of Power. So we are trying to see that from performance perspective, what kind of new opportunities we can explore, especially for big data and deep learning workloads. With this, let me conclude. So we discussed the challenges of accelerating big data stacks with HPC technologies. Especially, we presented some case studies in HDFS, MapReduce, and Spark. And then we say that OpenPOWER with InfiniBand platform is kind of promising, and we are able to get better performance through some careful designs and the tuning, those kind of things. And all the results looks promising. So hopefully we are able to enable the big data community and the deep learning community trying to use OpenPOWER plus InfiniBand plus GPT's kind of emerging hardware, so get good performance. We actually, along this direction, both Dr. Panda and I, we actually organized a workshop called HPBDC, High Performance Big Data Computing. This is like 4th year already, so if some of you in the research area or even in the industry, please feel free to join our conference or join our community. Thanks a lot.
Have you guys done any research on Cassandra as compared to what you've done here?
Yeah, so Cassandra, we actually didn't exactly modify their code, but we have a similar one called memory cache. So both of them like key value stores, right? So the only difference, Cassandra is based on quorum-based consistency model, but the memory cache is a little bit different. But from the application perspective, both of them like key value stores or long SQL database, those kind of things. So I think you just about whether do it or not. I mean, performance-wise, you could see similar kind of potential. This is what I want to give to you, the comments. Yeah.
In your design, when you change the protocols that are used in the native Hadoop interfaces, doesn't that change how a system would be secured?
Actually,
Moving away from HTTP with the SSL, the socket layer around
yes.
HTTP passing.
Yes.
Now you
Yeah.
exposed to an InfiniBand certificate, which is like a global, right?
Yes. This is a very good question. Okay. So, like I mentioned earlier, the default MapReduce during shuffle, they're using the HTTP protocol. Okay. And with HTTP protocol, you probably can enable HTTPS, like with security support, right? That's a good point. So because we bypass that, so we are kind of using RDMA-based protocols. So of course, it's not HTTP. Okay. But RDMA has its own security guarantee. So for example, all those data transfer, we didn't go to details. They have some concept called key. As long as you get a key, you can do access. Otherwise, you cannot. Okay. So there's different kind of mechanisms to provide security support. Maybe Dr. Panda can give some more explanation.
What he's trying to say is that as long as the InfiniBand environment is secured, we are not violating anything. Okay, so we are just following the InfiniBand protocols. That's all. Okay, and then the same security is
But
continuing.
it's not a multi-tenant security model, right? It's like
Actually, it's possible, right? For example, let's say if you are using running your jobs, you take a different key than me. Okay, we have different keys, so you cannot access my memory. I cannot access your memory because we have different keys. But it's different than HTTP security. That's true.
No, thank you.